I recently read about this enormous high voltage transformer at a substation, and on the surface it seemed totally fine.
Right.
The operators ran all their usual checks. The thermal cameras, they showed no heat. Vibration sensors were completely steady.
All green lights.
Exactly. But inside, that machine was, well, it was basically screaming, broadcasting this invisible distress signal that a catastrophic failure was coming.
It's the ultimate electrical secret, really. And those signals are just operating way outside the human sensory range.
Absolutely. So today we're going to do a deep dive into electromagnetic interference, or EMI, monitoring. It's this really revolutionary non-intrusive technique. Our mission is to figure out how we can listen to these electromagnetic whispers to predict major industrial problems, like insulation failure, way before the conventional methods see a thing.
Okay, so let's unpack the core physics here a little bit.
Please.
Whenever you have an extremely rapid change in current, and I mean, we're talking near instantaneous, you will generate high-frequency electromagnetic waves.
High frequency, like radio waves?
Exactly like radio waves. We're talking about signals in the RF band, so
Yeah.
hundreds of kilohertz all the way up to hundreds of megahertz.
So what kind of event inside a stable, massive generator could possibly produce such an incredibly fast jolt of electricity?
Well, the key fault mechanism here is something called partial discharge, PD for short.
Okay.
This happens in the solid insulation materials. Think of the stuff wrapped around the big copper windings. Over time, these tiny microscopic voids or air pockets can form inside.
Ah, okay.
And when the voltage across that little void gets high enough, it ionizes the gas inside it. And that creates a tiny, temporary conducting channel.
So it's like a miniature lightning bolt.
That is the perfect analogy. It's a miniature self-extinguishing lightning bolt.
And that must be unbelievably fast.
Precisely. That whole discharge event lasts only maybe 10 to 100 nanoseconds. And it's that incredible speed that generates the distinct high-frequency energy we can detect with EMI sensors. And what's really crucial here is that these tiny events only dissipate milliwatts of energy.
So not nearly enough to create heat.
For a long, long time. Thermal detection won't see that for months, maybe even years. EMI monitoring gives you this enormous head start.
Okay, but then if the signal is that faint, how do you keep from just getting a ton of noise? I mean, you've got radio stations, cell phones, other machinery. Isn't the environment just shouting over these whispers?
And that is the big engineering challenge, you're right. But the PD signal has a very specific repeatable signature, a fingerprint, if you will.
Ah.
It really stands out against all that continuous ambient noise.
Yeah.
We use advanced filtering, sure, but the key is looking for patterns that repeat at specific phase angles of the AC power cycle. Finding those patterns is how we pull the signal from the static.
So we're shifting from detecting the consequence of the damage, the heat and vibration, to detecting the electrochemical cause right at the microscopic level. And that has to be the whole economic argument.
It absolutely is. Traditional methods only confirm damage when it's already pretty far along. And for these high-value assets generators, large transformers, a single unplanned failure can easily cost $5 to $10 million.
In equipment and downtime.
Exactly. Detecting that fault early turns a 10-day catastrophic outage into a planned, maybe 4-hour repair. It's a huge difference.
And leveraging all that data, all that high-frequency noise to find the pattern, that requires some pretty advanced data solutions. And this deep dive is sponsored by Embersilk. If you need help with AI training, automation, integration, or sophisticated software development, you should check out embersilk.com. They specialize in uncovering where agents can make the most impact for your business or your personal life.
The practical side of this is also a massive win. The deployment is often totally non-intrusive.
So it's easy to install.
Very. We use these simple high-frequency current transformers, or HFCTs. You can think of them as highly sensitive clip-on antennas. They just clamp right around the conductors.
So no plant outage needed for installation?
None at all. That just dramatically lowers the barrier to entry. It lets operators shift from guesswork, from rigid schedules, to precise condition-based maintenance.
So you're not just preventing failures, you're optimizing the whole system.
Precisely. And when you integrate this EMI data with the thermal and vibration readings you already have, you get this incredibly clear picture. It extends the life of our critical infrastructure safely and economically.
What's truly amazing to me is that we can go from detecting a subatomic event, this tiny nanosecond flicker of current, all the way to creating engineering solutions that stabilize the entire electrical grid.
Yeah, it's pretty profound.
We're really mastering these invisible forces, not just for safety, but to build a more efficient, more reliable future for everyone. If this deep dive helped you shortcut your research on EMI monitoring, remember to subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.